Hi folks, this here what you're looking at is my homemade vacuum chamber. It consists of a 200mm diameter 5mm thick acrylic tube and 10mm thick 200mm diameter clear acrylic flat end pieces. There's an O-ring at top and bottom to form the seal. We have a vacuum gauge on the top and a valve arrangement to let the air in and out. There's the vacuum hose connected to the vacuum pump, and I'm going to be using this to conduct some heat transfer experiments. So first off, I'm going to be using this infrared radiator, if you like. It screws into a standard lamp holder, and as you can see it's rated at 100 watts. So it doesn't emit any light at all, it emits pure infrared radiation. Next up we're going to use this one, which emits visible light radiation. Again, this is a 100 watt, and it's a neodymium daylight spot lamp. Both of these lamps are used for heating lizard tanks, to give them some warmth. So we're going to be shining them inside the vacuum chamber at a thermometer, just a standard household thermometer. So this thermometer did have some little plastic bars, like a little grill, going across the alcohol bulb there, but I've cut them out so that they're not blocking any of the radiation. So that will sit vertically inside the tank, inside the chamber, with the lights shining directly at the bulb. And I'm going to time it to see what the difference is between vacuum and atmospheric conditions, to see if there is any difference at all, and if it even heats up, because as you know, in outer space, in the vacuum, there's supposed to be so few gas molecules that heat transfer does not occur, or it's vastly diminished, and that's why things like satellites and the ISS don't melt, since they're operating in the thermosphere, which can reach temperatures of up to 2,500 degrees centigrade. I wonder what's going to happen when I put this thermometer in the vacuum chamber. Is there going to be sufficient gas molecules to cause a reaction between the heat and the alcohol within this glass bulb? Does it even need gas molecules? Any gas molecules at all to cause a reaction? Okay, so before we begin, I just want to have a look at some of NASA's information on the thermosphere. This first web page here is NASA Space Place, and I believe it's aimed at children. But if you scroll down to this section, it says the heat that won't keep you warm. The thermosphere lies between the exosphere and the mesosphere. Thermo means heat, and the temperature in this layer can reach up to 4,500 degrees Fahrenheit. So if we convert 4,500 degrees to centigrade or Celsius, we're getting 2,500 degrees centigrade. Since all the other web pages are in Celsius, I've just converted this one to Celsius as well. So 2,500 degrees Celsius. If we go to this NASA page called Solar S'mores, this explains and talks about the solar cycle and it being 11 years. And if you scroll down to this section, it says the solar cycle has a big effect on the thermosphere where satellite drag takes place. During solar minimum, the gas temperature in the thermosphere is around 700 degrees centigrade. That's high, but not nearly as high as the temperature during solar max. When the sun is active, high levels of solar EUV raise the temperature of the thermosphere all the way to 1500 degrees centigrade. So why the big discrepancy? 1500 degrees here at solar maximum to 2,500 degrees centigrade or 4,500 degrees Fahrenheit on this page for children. It's 1,000 degree difference. If we carry on, it says if you were to hang out in the thermosphere though, you will be very cold because there aren't enough gas molecules to transfer the heat to you. So in the context of this paragraph, they're saying although it's 4,500 degrees Fahrenheit or 2,500 degrees centigrade, if you were to hang out in the thermosphere, you would feel very cold. Okay, so very cold in 4,500 degree heat. So if we go to this NASA web page, staying cool on the ISS, and we scroll down to this section, it says without thermal controls, the temperature of the orbiting space station's sun-facing side would soar to 121 degrees centigrade. So 121 degrees centigrade is sort of beyond human comfort temperature. So we wouldn't actually feel really cold. Although it does say while thermometers on the dark side would plunge to a minus 250 degrees Fahrenheit or minus 157 degrees centigrade. So it would be cold on the dark side. We would feel that as being cold, comfort-wise, minus 157 degrees centigrade. But they're not talking about on the dark side on this children's web page. They're talking about being out in this 4,500 degrees Fahrenheit and it being really cold. So there seems to be discrepancies all over the place when it comes to temperatures within the thermosphere. So take a look at these experiments and make up your own mind. Okay folks, this is test number 1. This is using the infrared only heat source. So it's attached to this lamp holder. The thermometer's in place just there. I'm going to slip this vacuum chamber over the top, but leave it at atmospheric pressure for test number 1. I'm going to turn the light round once I've placed it over. This light is preheated, or this infrared heat source has been preheated now, so we don't have to waste any time in it heating up. So here goes. Okay, let's turn the heat around. We'll place it sort of in the direction of the bottom mercury container. we have a distance of 57 millimeters, 58, something like that. So we're going to start the counter at 22 degrees. Okay, we'll stop that at 25 degrees and we'll do the same experiment under vacuum conditions. Okay, ready for the same experiment but in a vacuum. So, switch the vacuum pump on. Okay, we've got a vacuum. I'm going to turn this handle, turn this valve off. Now, you see there's a gap between the thermometer and the edge of the vacuum chamber. So I'm going to turn the pump off. And spin the light back round, which is preheated again. So it's approximately 57. That's not bad at that. Got a starting temperature of 20 degrees this time. So we'll take it up to 23. Okay, I'm going to say that's 23. Doesn't look like it's quite straight pointing at the thermometer, but it's not far off, as you can see. We still have the vacuum. So I'm going to let the air back in. Okay. Okay, this is the visible light experiment in atmospheric conditions. So I'm just going to place the vacuum chamber over the top again. And we've got a distance of should we say, 65mm to the centre. So I'm going to switch the light on. And we have a starting temperature of 22. Okay, we'll stop that at 30. So it started at 22, and as you can see, it increased much quicker with visible light. Okay, now let's try the same in the vacuum. So finally, we've got the visible light into a vacuum experiment. So I'm now going to turn the pump on. Okay, we've got a vacuum. We'll close this valve. Okay, that's closed. And the vacuum pump off. Okay, I moved that slightly with the valve, it's a bit slippy on the table. I'm just going to move that back. Let's get a distance on there. Again, it's about 65 to the centre. Still got a vacuum. Let's turn the light on. Okay, we've got a starting temperature of 22 again. Okay, we'll stop it at 30 again. Still got the vacuum. And I'm going to let the air back in. Okay, next up I'm going to be heating up this piece of matte black plastic that I've got fixed in there alongside the thermometer. The thermometer is just really as a gauge as to when to stop the experiment. I'm going to be focusing the light straight at the black plastic. So this is first experiment is going to be done in atmospheric pressure, and I'm going to use this digital infrared thermometer to take a temperature reading before the experiment begins. So if I rest it on the table, so I'll get it in the same place every time that I do the test. It's a little tricky to do this with the camera. Okay, so we're getting 20.4 degrees, 20 degrees let's say, in the centre. Okay, let's place the chamber over the top. Okay, we can see there's a gap between the edge of the vacuum chamber and both the thermometer and the plastic, and of course we're at atmospheric pressure. So I'm going to put the light in front of it now. And I'm going to use the digital thermometer as a gauge as to how far the light is away from the vacuum chamber. So as you can see, I can move that a slight bit closer. Okay, that's going to be the gauge for the distance. We have a starting temperature of 21 degrees. So let's turn on the light. Okay, I'm going to stop that there, folks. I'm going to quickly whip the vacuum chamber off and get another temperature measurement. Okay, in the centre it's a bit erratic, but it looks like about 50. Obviously dropping all the time, but you see the sort of region we're getting into. Okay, let's try in the vacuum. Okay, now for the vacuum experiment. So we've got that at 19.7 to the centre. So almost the same. And we've got 21 degrees at the minute, but I've got to pull a vacuum first. So it might change a little bit, but let's see. Okay, here goes. Okay, we've got a vacuum. Turn the valve off. Turn the pump off. Okay, we've still got the vacuum. Let's spin the light round. See, we've got the same distance. Starting temperature is 20. So let's turn the light on. So we started at 21 last time, I got up to 27, so we're starting at 20, so we'll go up to 26 this time. Okay, I think we're there. I'm going as quickly as I can get this air back into the chamber and measure the temperature. Again, it's a bit erratic. But it's exactly the same region of temperature as in atmospheric conditions. So in conclusion, my 100-watt light bulb was able to heat a piece of black plastic to 50 degrees centigrade in a vacuum. If we take what NASA says, the ISS on the sun-facing side will reach a temperature of 121 degrees centigrade, which is a little over double of what I was getting the plastic to reach, and that is with the addition of ultraviolet, X-ray, and the heat source being the sun. So if you remember back to a couple of years ago,
there was a craze, at least here in the UK, of people buying patio heaters, infrared patio heaters. Lots of pubs and bars bought them and put them outside so that customers could sit and keep warm. There was little point in providing convection heaters to heat the air, since that would be really inefficient. The air would just, dissipate. The heat would dissipate, should I say. So they put these infrared heaters in, and these infrared heaters do not heat the air up at all. They only heat solid matter. So when the electromagnetic radiation touches a solid object, it excites the atoms start to move, and the body heats up. In the thermosphere, it would appear that we're told that the exact opposite happens, and that solid objects are not affected by solar radiation, and that gas molecules are the only things that are. So somehow they've switched it. They've said that the opposite occurs in the thermosphere to what occurs here on Earth. I think my experiment pretty much proves that that's not the case, at least in a small vacuum chamber here on Earth. Admittedly, it isn't the same environment, spatially, but it is a vacuum, and it may not be a perfect vacuum, but nor is space or the thermosphere. In fact, it needs to not be a vacuum. It needs to contain some gas molecules in order for this heating to occur. So it's been enough to convince me anyway that what they're saying is wrong, and I've not seen any explanation as to why the exact opposite happens in the thermosphere in comparison to what happens here on Earth. I've just not found anything that explains why this may be. Anyways, I've been working on some other experiments in the vacuum chamber. They're taking quite a long time to do. Quite a lot can go wrong, and does go wrong. It's quite difficult to get everything done in one take and remember to sort of film everything. I've done the best I can. So I hope you enjoyed it. More to come in the coming months. Thanks for watching.